In my talk, I want to show you a possible way we can use a gravitational wave to get some information about the common envelope, especially for massive stars. So we know that we are in the era of gravitational waves, and thanks to LIGO, we have detected the merger of at least black holes binaries and double neutron stars binaries, maybe black holes and neutron stars. We also know that now black holes can be very massive, but the point is how we can form such a system that can be able to merge in less than a Hubble time. Here I show you a schematic representation of the possible evolution channel that lead the massive binary to the formation of either double neutron stars or black hole neutron stars that merge in less than a Hubble time. As you can see, the evolution, there are many physical processes involved in the evolution of binary systems, and surprise, one of them is the common envelope. In particular, the common envelope is essential to shrink binaries, otherwise that otherwise will not be able to merge. Since I am a population synthesis guy, I use population synthesis simulation to study how different physical processes can impact the formation of and the demography of compact object binaries. So here I just want to summarize, describe the code I mainly use, which is MOPSI, an updated version of the famous BSE. In particular, in MOPSI, we include the prescription for core collapse supernova, for pulsation pair instability and pair instability, and the state-of-the-art stellar winds. For the last point, in MOPS we include the dependence on the Eddington factor as reported here. In practice, we have that when a star approaches the Eddington limit, its mass loss becomes almost insensitive to the metallicity. And here on the left, you can see the mass spectrum of the compact remnant as a function of the initial mass for 8 different metallicity. And there is a strong dependence on the metallicity. So, namely, the lower the metallicity is, the higher the maximum mass of the black holes we have. So, here I summarize the models I'm going to describe you. In particular, I consider 3 different values for the efficiency of the common envelope, 1, 3, and 5. And I consider also 2 different prescriptions for the distribution of the natal Higgs velocity. And important, we assume that we force all S-prime gap donors to merge during the common envelope. This is justified by the fact that such stars doesn't develop a steeper gradient between core and envelope. So here I show you the merger efficiency as a function of the metallicity, the progenitor metallicity, for all the type of compact objects. And I define the merge efficiency as the total number of mergers over the total mass of the population. To make for example, if we have 10 mergers in a population of 10,000 solar masses, the merge efficiency will be 10 to the minus 3. The interesting thing here is that we find that for both black hole binaries and black hole neutron stars, there is a strong dependence on the metallicity. We have a higher efficiency, a higher merger efficiency at low metallicity. Instead, for double neutron stars, we don't see such strong effect due to the metallicity. But double neutron star seems to be more sensitive to the value of alpha and also the prescription for the supernova kits. We know one thing we can get from gravitational waves is the local merger rate density. So, starting from my merger efficiency, I try to estimate the local merger efficiency. To do that, I consider I combine the star formation rate as a function of the redshift with the metallicity evolution across the cosmic time, and of course with my merger efficiency. And here you can see the results for double neutron stars, black hole neutron stars, and black hole binaries. The points represent the 6 different simulations. And what I want to know is that for, the shaded area are the 90% interval confidence inferred by the LIGO-Virgo collaboration. Still, of course, this is based only on a single merger, a single event. We see that we can match the inferred value only considering high alpha, or both high alpha and low natal kick velocity. The error bar are the range, the maximum range we have if we consider, instead of evolution of metallicity across the cosmic time, but if we consider a constant value for the metallicity. So we can see also, the important thing here is that we see that in order to match all the local merger rate density with a single value of alpha, we need a high value of alpha. So playing the same game, we can estimate the merger rate density not only in the local universe but at different redshift. And here is the results for double neutron stars and black hole binaries. The interesting thing here is that while for the double neutron stars the different models produce huge differences in the local universe, for double black holes we have that the larger differences are in the past, so at high redshift. So with the in the future with the power of the new gravitational wave detector, we will able to reconstruct the merger history, and it will help us to better discriminate among the models. So to conclude, we found that with high value of alpha we can reproduce the merger rate inferred by LIGO-Virgo collaboration, but a possible explanation that can be that different systems may have different common envelope efficiency. And finally, I want to point out that with the new detection, so the increasing number of observations and the sensitivity of the new detectors, we will be able to reconstruct the merger history, and I think it will help us a lot. So, thank you.
We have some time for some discussion. Questions?
Maybe just a quick question. So you used alpha 135. What happens if you use alpha less than 1?
Less than 1. Okay, here I don't have the results. we did a simulation for alpha less than 1 for black holes, and we don't find a lot of difference here. We
For alpha less than 1?
For less than 1, yes, alpha 0.1.
So, just in general, then, what's your reason to use alpha more than 1?
More than 1, because we found that only with alpha more than 1 we are able to match
I guess Natasha's asking sort of how are you accounting for the energies?
Okay.
What energies? I mean, how do you calculate your binding energy, for example?
Alpha more than 1 means there is no energy conservation, there is no energy creation.
Yes, in evolution synthesis we use the alpha formula. So we impose, we don't do assumption of the energy, because we put every our knowledge in alpha.
But you shouldn't violate energy conservation. That's referring to. So you must be invoking some other energies then.
Yes, of course. There must be, but we don't
What
know
are they?
from where.
So I guess it's not really alpha lambda. Yeah. So you take lambda from somewhere else, so you say alpha lambda.
Alpha is 1, and the lambda is tabulated. We
So
use
you
the
tabulated
solid.
lambda.
Okay, sorry, I didn't understand.
So then, just to be clear, right? So if you have very small alpha, you don't get the double neutron star. Is that right? At the proper rate.
Yes.
And why is that?
Because for small alpha, we most of the system do not survive.
Right. Any other questions, comments? Right. Okay, you set up.
Maybe too fast.
Here.
Right?
Yours, that's, I didn't really work on it too much.
Sorry?
You didn't really work on it too much. Yeah, he had a lot of, suffered a lot from political, yeah, a lot for like, putting him under bad list. Giving grants, funds, giving back to kind of like him like a conduct denier or something.
Oh, yeah. I mean, he is kind of.
Oh, yes.
I mean, he's not a complete winner.
Yeah, he's not the classical climate denier.
But the problem is, you see, as I try
Here?
to talk to this,
Okay, so which
he's one of these big time.
this thing right here?
They're coming to the States in order to testify in Congress to like these crazies. And because they're looking for somebody to testify. And, you know, I said, it's a double-edged sword.
here?
This is mechanism for
Oh, God. All right. Okay, so.
loose connection.
No, it's not loose connection. It's just like it's a Linux machine. So
Why don't you set it so it just mirrors the display?
you just tried, it didn't work.
To be able to say that
Right.
that's the mechanism for eventually.
Okay.
Just use these spots change, you know, actually get it.
So the PDF.
Yeah,
All
right.
right.
Came to that experiment like in Copenhagen a couple of years ago.
Harlan, this paper we wrote was
Very long.
people that claim it had to be eruption because it looked like type 2P supernova, and basically we pointed out you can get exactly the same color temperature from radicals, just looking at just having a very optimal wind. So we wrote this paper here. He came to visit when he was actually over to testifying, and we got working on that, and then that's the last thing I worked on with him. Yeah, it's a unfortunate thing that.
Apologize for the technical difficulty.
Some both sides, you know, both ends.
Well, he's probably gonna be on the chairman of the department for another year or so.
Yeah.
Hopefully he can get back when it's
Yeah. Well, I sent it to him, this paper I did last year.
Oh.
With
Oh, yeah.
Also, I did some papers for anyway, if we have some obviously it was pretty occupied.
There we go. There you go.
So I'm interested in the life curve of transit, common envelope.
Use,
However,
sorry, use the microphone.
Yeah, you can mic.
well,
Don't hold a second.
I'm interested in the light curve problem of common envelope. However, I find it's a very complicated problem. So I go back to the similar problem of it's not playing full.
Oh, so you did this with Brian? Yeah. I didn't even realize that. I do remember that.
Oh, yeah.
I had some good discussions with my daughter, who lives in Toronto.
Yeah. So I go back to the similar problem of AGB star, which also has a very large amplitude of light curve. And let's start with what is AGB star. In a HR diagram, AGB star lies in the right up corner, which is cool and high luminosity. It usually drives the wind. And the bolometric luminosity actually variation is very small. And however, if you look into the optical band and its amplitude, this is a light curve of Myra. Its amplitude may be 7 or 5, 5 or 7. And that means, but as you go deeper into the long wavelengths, the amplitude of the variation gets smaller and smaller. A typical period of this variation is 200 to 800 days, and the mass loss rate of the HB star could be 10 to the minus 8 to 10 to the minus 5. Their velocity could vary, usually lies within 5 to 15 kilometers per second. And a schematic structure of the HB wind is there is a core helium with helium or hydrogen burning shell, and it's mixing in an envelope. But at the top of the envelope, there is a region that goes pulsation. It's pulsate. And this pulsation is going to create shock in the atmosphere, which is outside the convecting envelope. And the shock will cool down to where dust forms. And then it forms a wind, a dust-driven wind. Dust usually have higher opacity, but it's also frequency dependent. And the dust will absorb the different wavelengths of photon differently, and that creates the amplitude in different band we see. And we model the star from the piston, and the three major value that characterize the piston, the inner boundary of the star, is the amplitude and its period and its location. If we have the information of location, we use the MESA code to pick out the value of its density and temperature. Okay. Another big problem in this in the dust-driven wind is certainly the dust. So dust forms usually at 1300 Kelvin, and is radiative, absorbing the radiative transfer from the inside of the star, and then it gets accelerated and bring the gas together. The MESA code could generate like the HR diagram of a 1.5 solar mass star with the initial Z of 0.02, like this. And we pick the model, we set our model, what is marked with the red star there is effective temperature and photosphere radii, luminosity, and mass are listed there. And then we pick the distance location to be 255 solar radii, and that's where the density is this, and the temperature is 8,000, more than 8,000 K. At this temperature and density, the gas is actually partially ionized. So we take that into account, which is the equation of state thing. And then we go on to talk about the dust. So this is dust with me model. We consider the dust as a distribution of spherical particles, and with a distribution that is the same as the ISM. And we consider three kinds of dust. As you can see, as the ion increases, the opacity increases at longer wavelengths. So ion can absorb the opacity at longer wavelengths. This is 1 micron. So what we see, the large amplitude in V band is this where the short wavelengths getting absorbed, and the L band is low opacity. So the low opacity photon just get out without interacting the dust. And so we put that boundary condition into a simulation, and we let the gas getting out, and also the gas will recombine in the atmosphere, and it cools. Then it deposited the energy into the radiation, and the radiation will further interact with the dust outside. And the blue dots shows the light curve, the luminosity of the star with realistic equation of state. And the red dot shows the light luminosity with gamma equal 5/3. This black line is showing the phase of the piston. The piston is varying sinusoidally. So you can see there is a difference in using different equation of state, which is easy to understand. And then let's see what is the optical depth of the V band from the photosphere to observer. So the optical depth changed from almost to 100 to optically thin. So at this point, you will see the surface of the star. However, here you will not see it because it's optically thick. And that's why we see large amplitude in the V band. One thing to note is that you don't see the star here. However, you see the emission of dust in V band, continual line. And then let's see the L band. The L band is very also large, but the peak is only less than 1. It's roughly optical depth is 1. At that point, I think you will still see the star, and it's optically thin when the oscillation is in some phase. The red is showing the 5/3 perfect gas. So actually, the realistic gas and perfect gas has a lot of difference, both in light curve and mass loss rate. This is the mass loss rate. And it's 10 to the -8, it's 10 to the -7. So the velocity, wind velocity at 10 AU, I recorded it as km per second, and we find that it's within the range, reasonable range, but the realistic gas will produce lower wind speed. And this is the equation of state that we use. This curve are the realistic equation of state, and the gamma gas is shown in the straight line. And their difference is huge, actually. You can tell at some point it could be 1 order of magnitude bigger. And at 8,000 Kelvin, actually the gas is only partially ionized. So we solve the equation of state analytically on this divided equation of state phase space, and the high density part could have coexistence and hydrogen combined. But this is ionization, and we take that into consideration analytically. And so to summarize, I think the volumetric luminosity variation could be connected by the cooling process. So you cool the gas and deposit those energy into radiation. And dust formation and destruction of the AGB star vary differently at different band because that dust have different opacity at different wavelengths. And equation of state is playing a role in the AGB wave. So thus it could be in the homeland.
So it's 2.
Time for a few comments. Questions? So I'll take my role as moderator to ask questions. So your dust is basically much further out in the atmosphere, right? Like the surface is at almost 3,000 Kelvin, which is above the dust sublimation temperature.
Yeah,
right. Sure. So like what drives that stuff out above the polar station?
So actually, dust forms around 2 to 3 stellar AGB stars radii, and you need to push the gas there. So that shock, the amplitude at the bottom is only 5 kilometers per second, but when you form a shock, the shock could be accelerated to 10 to 15 kilometers per second, and that could reach the upper layer of the atmosphere, and where it does to form.
Okay, and then your mass loss rate is not all that different between the dust case and the non-dust.
No. They all have dust. There are differences in the equation of state. Yeah, also
so
the
account for recombination energy or what?
Yeah, that's the cooling of collisional collisional cooling and recombination cooling from the hydrogen, and then it's released in radiation.
So then would the statement be correct then that recombination doesn't play such a huge role in AGB stars?
In the
terms of mass
you can
rate?
see that the luminosity, total luminosity doesn't change too much because the baseline here is 4,000 to 300, but the peak is only 200 more. So in AGB star, the luminosity total luminosity doesn't change too much. But you still see that the different band, they are changing much. However, in the common envelope, I think this amplitude should be much more higher if you consider, because it's a full, if it's a full ejection, it recombines and the released energy could be very huge. This is only a pulsation, going back and forth.